My name is Anisa LLaveshi, and I will present this. My name is Anisa LLaveshi, and I will present this work done in collaboration with Utku, Sirin, Anastasia, Ailamaki, and Robert West on how we can accelerate the B+tree search operation by using simple machine learning techniques. So, in-memory systems have eliminated much of the overhead of the disk-based systems. Being that they keep all the data in main memory, there is no need for the buffer pool structure, so this has been eliminated. In addition, they have lightweight logging mechanisms and lightweight concurrency control mechanisms. So it would be interesting to actually see where does the execution time breakdown of an in-memory LTP system. On the plot on the right, we can see the execution time breakdown of state-of-the-art in-memory LTP system, Silo, when run on two micro-benchmarks, a read-only micro-benchmark and a read-write micro-benchmark. As we can see, more than 60% of the time is spent on the index search operation. Thus, it is obvious that index search dominates the execution time of in-memory LTP systems. During the past years, a lot of research work has been done on improving the performance of index structures. Recent work has suggested that we replace the B+tree index altogether with a set of recursive machine learning models which, given a key, can predict the position of this key in the index structure. While they have shown that this method can actually highly accelerate the B+tree search operation, they use a mixture of machine learning models, among which even complex models like neural networks. In addition, they assume only a read-only scenario. And also they use only clustered index organization, which means that the data is stored in a contiguous memory address space. This makes it rather hard for this structure to support inserts. In this work, we propose a different and a simpler solution. We suggest using linear regression models in order to accelerate the B+tree search operation of a B+tree which also supports inserts. So, given a B+tree, we create a model, a linear regression model for each inner node in the B+tree. Thus, these models will then be used to predict the node where a key will traverse in the next level during its search path. So, given a key, this key will go through a chain of models, one model per each level. And each of these models will predict the node where the key will traverse in the next level. Thus, in the second to last level, this last model will predict the node where the key will reside in the leaf node level. So once we have the node number of the leaf node where the key resides in the node level, we can directly jump to this leaf node, and we can search inside the leaf node. For instance, in the B+tree shown in the slide, we can see if we want to search key number 17, we have first it goes as input to the root model, and then the root model will predict that the key will traverse in its path the child number 2. So this model will predict number 2, and then once the key goes as input to the model number 2 in the second level, then it will predict that this model will predict that the key resides in the child node number 3 in the leaf node number. So once we have this node number, we jump to the node and we search inside the node. It is possible that there will be mispredictions and the leaf node number will not be the correct node where the key resides. In this case, the key will be positioned in one of the neighbors of the node. So it will be still in the neighborhood, and we can search in the neighborhood of this predicted node. We use different features and labels depending on the data distribution that we have in the B+tree. So as features, we use simply the search keys, and either the search keys or the logarithm of the search keys. For labels, we actually need, for our method to work, we need an identifier for each of the nodes in each level. So this has to be unique. So what we do is we number the nodes consecutively from left to right in each level. So the nodes will have a number from 1 to n, where n is the total number of nodes in that level. So we use these node numbers as labels. Either simply the node numbers or the logarithm of the node numbers. So given a set of training data, which is a set of keys and node numbers. We build a linear regression model for each inner node in the tree. And these models then will predict the node number that the key will traverse in the next level in its search path, even for unseen keys, for future unseen keys. When there are inserts in the database, there are a lot of, in the index structure, there are a lot of challenges that are brought. So the inserts will change the B+tree structure. So at first, since there will be new data coming in, new nodes will be created. These nodes will either contain new data or will contain data that used to be in other nodes previously in the B+tree. In addition, these nodes will not have a corresponding model and they will not have a corresponding label either. Thus, these nodes will not be accessible during the prediction process. So in order to mitigate the deterioration of the models in the presence of inserts, we implement an adaptive training algorithm. At first, our system will serve insert queries as normal insert queries in a B+tree, and it will serve the search queries with prediction, as I just explained previously. So during the search queries, we'll keep track of the behavior of our system, of the accuracy of the models. And once we see that there is a deterioration in the performance of the models, we will decide that it is time to retrain. We start the retraining process, and during this retraining process, there will be two parallel threads of execution. On one side, the B+tree, our system will continue serving the insert queries and the search queries with prediction, as I just explained, using the old models. However, on parallel, there will be a retraining process. So new data will be collected from the new B+tree, from the changed B+tree, and new models will be created for each of the inner nodes in the tree. So during this, once this process is over, once we have the new updated models for the changed B+tree, we will swap the new models with the old models, and we continue serving every query, the insert and the search queries, using the new models. In this way, we are able to update the learned models, also in the presence of inserts and as the structure of the B+tree changes. We use a B+tree, to evaluate our system, we use a B+tree index, which has unsigned 64-bit integers as keys and values. We use different fanouts of 50, 100, and 500, but we'll show results only for the fanout 50. We use 4 different data sets in our experiments. We use synthetic and real-world data. For synthetic data sets, we use a uniform data set, which has and we buckload the tree with 300 million keys, which amount up to 5 gigabytes. And again, for a synthetic data set, we use skewed data with data generated from a Zipf distribution with 2 different skew factors of 0.25 and 1.0. Again, we buckload the tree with 300 million entries. We use also a real-world data set, which is the IMDb movie data set, and more specifically the title data set, which consists in 2.5 million entries. We use different metrics to evaluate our system. We use accuracy, and accuracy represents the ratio of the correctly predicted nodes over all the predictions that the system makes. The average misprediction distance evaluates the distance of the mispredicted node from the correct node number. This is averaged over all the predictions. And the search time represents the time that it takes our system to perform a search operation. Now I will present the accuracy results of our system. So we use 2 different metrics to evaluate the accuracy of the system, and it's again accuracy and the average misprediction distance. We can see on the plot on the left, on the x-axis we have the 4 data sets that we use, and on the y-axis we have the accuracy ratio. The accuracy ratio can vary from 0 to 1. We can see how the accuracy is over 80% for all data sets that we use. This means that in our predictions we are 80% correct, and we find 80% of the time we find the correct node where the key resides for a key that we are searching. On the graph on the right, we can see we have again on the x-axis the 4 data sets, and on the y-axis we have the average misprediction distance. We can see how the average misprediction distance is 1 for all data sets that we use. This means that even in the cases where we mispredict by at most one node. Thus, the key that we are searching, and we have mispredicted this position in the leaf level, means that it is in a direct neighbor of the node that we have actually predicted. Thus, overall, we have higher than 80% accuracy on all the predictions and very low misprediction distance. Now I'll present the performance results of our system. Our main goal is to improve the performance of the search operation, and this plot will show us how successful we are. Actually, the results that I just showed regarding the accuracy are an indicator of this. We can see again on the x-axis the 4 data sets that we have, and on the y-axis we have the search time of our system normalized over the search time of a normal B+tree. So we can see how for uniform data and for the real-world IMDb data set, the search time is accelerated up to 57%. This means that the search time that our system takes, the time that our system takes to perform a search query is 50% faster than the time that a normal B+tree takes to perform such a query. In addition, we can see how for skewed data, the search time is accelerated up to 33%. The reason that there is a lower improvement in the search time acceleration for the skewed data is because, as I explained earlier, we sometimes log transform the data, and and for skewed data sets, we log transform the data, and taking the logarithm and the exponential of the data are expensive operation and time consuming. Thus, this results in a lower acceleration of the search time. However, we can say that overall, the search time of our system is 33% to 57% faster than the search time of a normal B+tree. Lastly, I will show you how fast we can adapt to a changing B+tree structure in the presence of inserts. We backload the tree again with 300 million entries, and we run an alternating workload of 50% searches and 50% inserts. So we run these experiments for uniform data and for skewed data with skew factor 0.25. We can see on the plot on the left how on the x-axis we have the time, and on the y-axis we have the accelerated search time that our system takes to search 10,000 keys. So we keep in mind that as time increases, there are inserts being performed in the system. So we can see how at first the search time is quite low for both uniform and skewed data. And as there are inserts present in the system, the search time gradually increases. After around 400 million inserts, which means after doubling the size of the tree, we start the retraining process. We decide that the search time has deteriorated and that the accuracy of the models has deteriorated, and we start this retraining process. We can see how the retraining process takes a very short amount of time compared to the pace of the queries. So after the retraining process is done, we can see how the search time drops. And as there are inserts again present in the system, and as the B+tree structure changes, we can see how it gradually increases again. On the plot on the right, we can see again on the x-axis the time, and on the y-axis the average distance of the system, which is, as I explained, the distance of how far are we from the correctly predicted node in cases of misprediction. So we can see how at first this distance is very low, and as time increases, and as there are inserts present in the system, the average distance also increases. So we have decided in this case that the threshold is where we start retaining is actually going to be this average distance. And when this average distance passes the threshold of 1, we started the retraining. So we can see again how after retraining is done, the average distance drops, which means that we again start correctly predicting the leaf node numbers. So overall, we saw how the learned models are very robust against inserts, because as we saw, it needs a lot of inserts in order for the accuracy of the models to deteriorate. In addition, we also saw how the retraining takes a very small amount of time. And lastly, we saw how linear regression has very high accuracy, around more than 80% accuracy in predicting the correct leaf node numbers where a key resides. We also saw how B+tree search time is accelerated from 33% to 57% using our system. And lastly, we saw how the models are robust against inserts and can adaptively be updated in the case of deterioration. Thank you for your attention, then I am open to questions.
Just have a quick question and then go into
Hey, I had a quick question. In the beginning, you mentioned in-memory systems. So, how is this relevant to in-memory systems? I believe your search can be optimized even for disk-based systems, right? At the end of the day, you're applying linear regression. So, what's specific about in-memory databases that's relevant to your work?
Thank you for your question. As we saw, this is relevant because we can see how the index search operation this is a breakdown graph of the execution time of an in-memory OLTP system. It's actually, if I dimension, is the state-of-the-art system silo. So, as we can see from this graph, the index search operation takes more than 60% of the time of these in-memory systems. So, this means that this is the bottleneck of the performance of the in-memory OLTP system.
Have you done any study over disk-based tables as well? Like, would your system, would your algorithm sort of help in disk-based tables at all, or you haven't necessarily done that?
Excuse me, sorry, I couldn't hear the question. Can you please?
So, have you done the analysis for disk-based tables as well, non-in-memory tables at all?
No, it's only for in-memory.
So, just a couple of questions over here. So, one is that what is the insertion rate you're getting, say, on the high-end like Amazon nodes?
I'm sorry, I can't hear. Can you please speak louder?
So what is the insertion rate you're getting, say, on machines on like Amazon high-end nodes?
When is the
insertion rate? How many insert records per second?
Insertion rate.
Insertion rate. It's 50% inserts and 50% searches, as I explained.
I just see the number.
Like how many percent?
I don't have those numbers.
You don't have them.
But yeah, we can calculate them. Around the time 2000, there are actually 400 million inserts which are made in the system.
So is it like 100,000 per second, or is it a million per second? What is the kind of thing you go after?
We just consecutively provide insert and search queries, provide 10 million inserts, 10 million searches. We don't depend that on time, and then we calculate the time.
Okay, so have you tried this one on Intel Optane, or is just all pure main memory?
Have I tried
Intel persistent memory.
Have you tried Intel's Optane drive?
No.
No, you have not. So have you compared this one with the Tokutech technology of the MIT from 4 years ago?
No, we have compared this only with the B+tree that we have implemented.
What about the black and BW trees?
No, we haven't.
Okay, those are your competitors.
No, BW is terrible.
Okay, Tokutech. I said that one first.
Yeah.
Okay, I said that first, but you said no. So
Thank you.
So let's try to get back here and now for the second, sorry for running forward.
The BW is everything. Only these skills.